So today we will learn about wind energy conversion system. A wind energy conversion system actually it is powered by wind energy and generates mechanical energy that sends energy to the electrical generator for making electricity. For wind energy, actually it's an alternative to fossil fuels, as you know, and it is plentiful and come under the category of renewable. It's widely distributed, it is clean, it's of low cost, and they do produces no emissions during operation, and they do uses only a tiny land area. The effects on the environment are generally less problematic than those from other conventional power sources. Figure shows the interconnection of wind energy conversion systems. Wind energy conversion systems converts wind energy into electrical energy by employing wind turbine and induction generator. To a multiple ratio gearbox, wind turbine is coupled with the induction generator. The major parts of a wind turbine are the rotor, the nacelle, and the tower. The generator and the transmission mechanism are housed in nacelle. It includes the generator, the gearbox, the drivetrain, the brake assembly. The tower on which a wind turbine is mounted is not just a support structure. Actually, it elevates the wind generator above the ground, and the blades and nacelle are mounted on top of a tower. Next part is the rotor. The rotor may have two or more blades. The kinetic energy of wind flow is captured by this rotor blades in wind turbine, and then through a gearbox it is transferred to the induction generator side. And the mechanical power developed by wind turbine is used to drive the generator shaft to generate electric power. So here you can see the shaft. It's a rod that connects the rotor blades to the generator, and its main purpose is to transfer the rotational mechanical energy of the rotor blades to the generator. And a wind turbine actually consists of two shafts, main shaft and the generator shaft. The main shaft, it is connected between the blade hub and input to the gearbox, and it usually rotates at low speed, so it is also called as low speed shaft. Then comes the generator shaft. It connects to the gearbox. It connects the gearbox output to the generator input, and it's rotate at very high speed equal to the rating of the generator, and it's called high speed shaft. So then the last comes generator. It is a device which is used to convert the mechanical energy to electrical energy. So coming to the gearbox, actually the slow rotational speed of wind turbine, it is converted to higher rotational speed on the induction generator side by help of this gearbox. So by using supervisory control, metering and protection techniques, the output voltage and frequency is kept within the specified range. We can use different control methods to either optimize or limit the power output of wind energy system. We can control a turbine by controlling the generator speed, the angle adjustment, and the rotation of the entire wind turbine. So to ensure the wind turbine is producing the maximum amount of electrical energy at all times, the yaw drive is used to keep the rotor facing into the wind as the wind direction changes. The yaw mechanism is used to turn the wind turbine rotor against the wind. The second mechanism is pitch control mechanism. The purpose of pitch control is to maintain the optimum blade angle to achieve certain rotor speeds of power output. The third one is whirling mechanism. The stronger the wind, the better output we can get. But if the wind is too strong, then a turbine can spin so fast and it destroys itself with turbine blades get teared off, the alternator get damaged by excessive heat, and many may damage occur for the tower too. So whirling is one method of preventing a wind turbine from spinning too quickly simply by turning the blades away from the direction of the wind. and it can be achieved either manually or it can be achieved automatically with turning the blades out of the wind. And this furling is mainly need for overspeed protection, for maintenance, and to protect the WTG components in strong winds, to reduce wear and tear, and to manage the output as wind speed increases. So basic process of wind energy conversion is to capture the wind energy and to convert that to electricity. So here you can see the rotor blades. So when the rotor blades turn, the shaft also turns, which makes the generator to produce electricity. So let's see the classification of wind turbine. So based on location, wind turbines are classified into three: offshore, onshore, and nearshore. Offshore means here the sounds are at least 10 kilometers away from the land. And coming to onshore, they are located in the land, especially in hilly areas. And nearshore means here it's located within 3 kilometers from nearest shore, or on water within 10 kilometers from land. And based on number of blades, they are classified into three: single bladed, two bladed, three bladed. And by and large, most wind turbines operate with three blades as standard. The decision to design turbines with three blades was actually something of a compromise. Because of the decreased drag, one blade would be the optimum number when it comes to energy yield. And based on axes, these wind turbines are classified into two general types: horizontal axis and vertical axis. A horizontal axis machine has its blades rotating on an axis parallel to the ground, whereas in a vertical axis machine, it has its blades rotating on an axis perpendicular to the ground. So there are basically two types of wind turbine: fixed or constant speed turbine and variable speed turbine. In fixed speed, the turbine works at some fixed speed, say 6 meters per second, and if the speed is less, it doesn't work, and if speed go higher, it tries to lower the RPM to match the RPM for the 6 meters per second. Okay, in case of variable speed, they can work at the range of its cut-in and cut-out speed. And this constant speed wind turbine, they operate approximately at constant speed as prefixed by the generator design and gearbox ratio. The control schemes are usually designed to maximize either the power output at higher wind speed by regulating the pitch angle, or capturing energy by controlling the rotor torque. And based on the control strategy employed, constant speed wind turbines are again subdivided into pitch regulated turbines and stall regulated turbines. So the difference mostly noticeable in high wind speed. Here in stall regulated system, they rely on aerodynamic design of the blades to control the aerodynamic torque. In case of pitch, they do use active pitch control for the blades. Here the figure shows a typical variable speed pitch regulated wind turbine system. Actually, it controls the turbine operation by two methods: by changing blade pitch or by changing the speed. The control strategies generally employed are power limitation strategy and power optimization strategy. In power limitation strategy, the output power is limited to the rated value by changing the blade pitch. This control strategy employed for wind speeds higher than the rated value, and it results in reduction of aerodynamic efficiency. In power optimization strategy, energy capturing is optimized by maintaining a constant speed related to the optimal TSR. This control strategy is utilized when the wind speed is lower than the rated value. But if the speed is altered due to variation in load, the generator might be overloaded for wind speeds higher than nominal value. The techniques like generator torque control are employed to control the speed and to avoid this problem. Variable speed wind turbine systems have the following advantages. They have low transient torque and are aerodynamically efficient. They are subject to less mechanical stress and have high energy capture capacity. They do not go through voltage sags or synchronization problems due to stiff electrical controls. The electrical system provides effective damping, hence no mechanical damping systems are required. So as compared to constant speed turbine, they have the following drawbacks, like low electrical efficiency, and they require complex control strategies and are expensive. We will see the power equation of wind energy conversion system, and the power in the area swept by the wind turbine rotor, it is given by the equation P is equal to half Cp rho a VQ, where P is the power in watts, Cp is the power coefficient, rho is the air density, A is the swept area of rotor blades, and V is the wind speed. Okay, wind speed in meter per second. So coming to power coefficient Cp, actually it's a measure of total energy extracted by rotor of the turbine, and it is given by power output from wind machine by power available in wind, and the value is 0.593, and for good design the maximum value is 0.35, and the value of Cp varies with rotor design and tip speed ratio. And tip speed, which is nothing but it is the relative speed of wind and the rotor, and has a maximum practical value of about 0.4. So it is represented by letter gamma. Gamma is given by tip speed of the blade by wind speed. So let's see the advantages of wind energy. Wind energy, it's as long as the wind blows, the energy produced can be harnessed and it will never run out. And this wind energy, it's a clean source of energy, and here this wind energy can be used directly as mechanical energy, or it can be converted into electrical energy, and usually it can be used in remote areas, and they can also be used for some other uses like farming, etc. So coming to the drawbacks, actually wind energy requires expensive storage during peak production time, and it is not constant like solar energy, and it requires large open areas for setting up wind farms. And these wind turbines, they are noisy and they will create noise pollution, and in terms of efficiency it's less when we compare with fossil fuels, and it poses a threat to wildlife. Birds do get killed or injured when they fly into turbines, and maintenance cost also is high, as they have mechanical parts which undergo wear and tear over the time. So that's all about drawbacks of wind energy. So with this we come to the end of the topic wind energy conversion system.